All right, so my name is Alexander, and I did my presentation on screening here. So just a quick outline, we're going to go through an overview of screening, go over how screens are classified, screening characteristics and quantities. Then we're going to go over the coarse screens, fine screens, micro screens, and then some screenings, handling, processing, and disposal. All right, so screenings is pretty much the first step in your wastewater treatment plant. It's used to get all your really large objects that could damage things down the line or clog other equipment. They could lead to reducing treatment reliability or effectiveness and contaminate your waterways if they actually get out of the system. Then your fine screens are further used to protect equipment from that are more sensitive to solids, and then remove materials that affect reuse of biosolids. What to consider when using or planning how you're going to use your screening. Screenings removal is really stinky. So not only do you need to look at the health and safety of your operators, there's your odor potential, and you pretty much have to get it out of there before you can dispose of it. And you have different disposal options depending on what your coarse or fine screens are. So your classifications of screens. Your coarse screens are going to have openings that are bigger than 6 millimeters. They're mainly used in preliminary treatment. Fine screens are from 0.5 millimeters to 6 millimeters. And they can be used in preliminary treatment, sometimes prior to sludge processing. And then micro screens, which have their openings are less than half a millimeter, are used to remove residual solids from treated effluent, so before it actually gets to your waterways. And here's just a little breakdown from the book. So pretty much under your coarse screens you have manually cleaned screens and mechanically cleaned screens, and I'll go over those in more detail in just a second. Screening's characteristics and quantities. So screening's retained on the coarse screens. Obviously, since the holes are larger than, or 6 millimeters, it's anything greater than 6 millimeters. It can be anything from rocks, branches, lumber, leaves, plastic, paper, tree roots, bottles, cans, rags, etc. I really wanted to show you guys some pictures of these, but I couldn't really find any that you could tell because it's just all mixed in together. And then your screening's retained on your fine screens. They're going to be small rags, paper, plastic, razor blades, grit, undecomposed food waste, feces, etc. And depending on the type of screening system and your sewer system and geography, you're going to find just a range of these. Obviously, after a rain or whatnot, you have a combined sewer overflow, then you're going to have all kinds of leaves in your on your screens. All right, so different type of coarse screens again. Manually cleaned coarse screens and your mechanically cleaned bar screens. There's 4 different types of screens that the book went over or into a little bit more detail. And then it went into detail on design of coarse screen installations. So we have the chain-driven screen. And there's really 3 different types of chain-driven screens. They all depend on whether or not they're actually scraping the front or the back of the screen, and then whether or not they come back around on the front or the back. So depending on which way they're traveling. Is that right? Yeah. Problems with these are that they have submerged sprockets, and obviously that's a problem if they go down, you have to do maintenance. You have to dewater the area around them, so there has to be a way to get those blocked off. And here's a few of the companies that actually produce these. Reciprocating rake screens, it pretty much imitates just what a manual screening, how it would be cleaned, just like a person raking over the screen. All maintenance is above the water line, and with these, the combined sewer systems, they're more likely to clog just because they are pretty much on a timer, from what I understood, that whereas other ones pretty much reached a load or whatnot, and then they started working. And here's a few companies that produce those. And then we have the catenary screen, which is front clean, front return, chain driven, but there's no submerged sprockets. So it's a lot easier to work on, but it also has a larger footprint. And a few of the companies that build those. Continuous belt screen. It's continuously self-cleaning belt. Actually can be used both as fine or as a fine or a coarse screen. Actually, when it's used as a fine screen, it can actually remove the need for a coarse screen upstream of it. And it also uses rakes. And there's a few companies that build those puppies. Here's your design equation for these screens, and I don't know what that little tiny VS squared is. That shouldn't be there. But pretty much it all depends on your head loss. So you want to still keep your water flowing here. So head loss is equal to 1/C, which is a coefficient of discharge for the screen. That's determined empirically. I think it was somewhere between 0.7 and 0.6. G is acceleration due to gravity, and then velocities are listed there. So your fine screens are screens for preliminary and primary treatment. There's 4 different types that, again, the book went into: static wedge wire screens, drum wedge wire screens, traveling band screens, and step screens. Then it went into a little bit of fine screens for combined sewer overflows and some design equations. So here's your static wedge screen. Actually, what happens here is, that's a pointer, your water comes up through here and comes down and then back out. So all your stuff is collected there. And those have to be cleaned with high pressure hot water, mostly to get out grease and oils and things like that. Your drum wedge wire screen depends on actually how it's going to be flowing through the drum, on how it's either, this would be tangential, is that right? Tangential screening as opposed to radial screening. And they vary depending on how they're going to be used. Most commonly, water comes from both sides and then exits through the screen. And here's a few companies that make those. Then we have the traveling band screen. It's used at the headworks or for secondary influent. And this actually goes through and collects everything on the inside and then drops it up here where it gets taken away. There's a few companies that make those. Step screen pretty much works as a filter mat, so the more that's on there, the better it collects more stuff. And then it just steps it up to a collector at the top. And then here are the 2 that are used for combined sewer overflows. Well, the drum screen we already pretty much went over, it's the same. Horizontal reciprocating screen is you have a horizontal screen, and then there's pretty much blades that go back and forth to cut everything off, and then you can tilt back the horizontal screen to get more surface area. And tangential flow screen has a chamber here, is your wastewater flows through it, larger solids come settle out. and your fine screen design equation here. It's pretty similar. Then your microscreens, they are usually used at low speeds, continually backwashed. Rotating drum screens are the most common. Their openings are only 10 to 35 microns. They're used to remove suspended solids from your secondary effluent or from a stabilization pond. And they range from 10 to 80% solids removal, averaging 55. And pretty much when you design them, you just need to know what actually is going through there. So you need a balance between how much the drum will actually hold and how long it'll wear, or how long it'll stand up to wear and tear. Okay. And pretty much you just need to do pilot plant testing for that. To get rid of the screenings, usually have conveyors or whatnot. They're either ground compacted and they're dewatered, and they're either hauled away to landfill, buried on site, incinerated if they're really big, or ground up and sent back. Here's where all the pictures came from. And I'm done.
All right. Great. Thank you, Wade. Appreciate that. There was just one thing from my presentation that I wanted to show. I found a video related to screening that is, it's always fun to watch videos, especially videos of wastewater. So, pop that.
Yep.
Thank you. No, you basically covered everything that was in the slides I was going to share with everyone, except for this little video that shows it in action. Okay, wait for it. There it is. If I remember correctly, this video doesn't have any sound. It's just the facts. So as you'd imagine, as Wade said, if you've got some of these parts underwater and it's a corrosive environment, then you're going to have some way to get access to clean it up. See, it's just scooping the debris and it'll go up the top of the screen and then into a hopper. That's the garbage in there. Put a GoPro right on there, straight to high action. So it gets to the top. There it goes, down the chute. All right, pretty exciting stuff. We'll leave it at that. Okay, so thank you again, Wade. Let's see who's next on our list. All right, E. Ready? Okay. Okay. Put this on your lapel as a microphone. Okay. Let me bring the lights up. You've got 10 minutes, and I'll give you a 1-minute warning when you're almost out of time. Okay.
Okay. I just have the 2-page on the test book, so maybe it's a little. And today I will introduce the coarse solids reduction, and there we use commutators and macrators and head grinders replace the coarse bar screen and fan screens, and theoretically they eliminate the mass and offensive task of screening, handling, and disposal, and particularly they also can protect the pumps against corrosion by rocks and large objects. They are very useful in the cold climates where well-collected screening are subject of the freezing. And they are referred to school of thought mentioned, and one is that once coarse solids have been removed from the wastewater, they should not be retained regardless of the form. And another one is that the once cut off the solids are more easily handled in the downstream process. And the shared solids often present downstream problems, particularly with rags and plastic bags, as they tend to form wrap-like standards. There is adverse impact includes closing pulp impeller, sludge pipelines, heat exchangers, and third is accumulating air differentials and clear mechanism. And the first is non-biodegradable materials adversely affect the quality of the biosolids that are to be the beneficial reused. And let's say this, and I make this table to show the difference about the commutators and macrators and grinders. And I think my macrator and the grinder have the same operation, just the macrator have the slow speed and the grinders have the high speed. And about the commutators, the main structure is a stationary horizontal screen, rotating or oscillating arm with a cutting teeth, and macrators and two sets of the cut-written assemblies with the blanks. Grinders had a stationary grid of the lower that includes the rotating assembly. And this is a picture showing the commutators. And you can see the big core solid can be this, how to say it, the cutting, I don't know how to say this. Is a roast and with the car teeth, and the solids will go this and will be the smaller trash and going through this way. And about macrators, and this is a slow speed grader, and there are the two tabs. One tab there has two counter rotating cutter, and like this, and the solids will go through this way, and this has the benefit that people didn't operate it and easier than the communicate. Excuse me. Its benefit, it has the many benefits than the commutators. And there is a video about that, and I will show you.
Is this the Muffin Monster video? It's
Yeah.
a good one if it's the one I'm thinking of. Okay, let's see.
Because I think it's a same operation with the macrator and the agenda.
Hi there.
Sorry.
Grinder can quickly reduce tough
The operation
sewage
like
solids,
that.
such as rags, plastics, wood, mops, and more. TM85.
And the operation like that, and I think this is a high-speed grinders, but the same operation with macrators. And another one. You can say it's how to create.
Oh, gee, oh,
It's a little creepy. Like this. So that's all. That's all. And there has another type of macerator like this. There has a here is a counter rotating cutter, and there has a flow, and there will go through, and the solids will go through this way and be the cart. And now I will talk about the defects. For these combinators, and there is operating problems and high maintenance. And for the macerators and solider after treating are not fine. I mean, it's if the solid goes through this way, but it's not cut very small, and it's not very uniformity. And for the grinders, and the defect is it needs large power, and it makes noisy than the other tools. About the design consideration, and there are many details about the design considerations, but it's not very necessary for this. It depends on the different situation, and you can have some details for the design. And this is all. So just this, because I just have the 2 pages in the textbook. Thank you.
Thank you.
Sorry, Mel.
That was very good. The only thing I have to add is we need to watch more of that macerator video. It's just, we'd be really remiss if we didn't look at the muffin monster, because that thing, they're smashing all sorts of stuff in there. It's not just oranges and soft chickens in this muffin master. Let's see here. They go all out with this baby. And the music's great too. Tennis balls, right? Awesome. Yeah, I want to do aerobics when I hear this. Yeah. When I see him do that, I just think, what if your fingers got caught? I mean, that's an intrusive thought, right? That's a problem they have. I think I already skipped past the belt. That's always the impressive, is it just chews up the buckle and the leather. This is like 8 minutes long. We won't watch the whole 8 minutes, but let's see, what's some of the other stuff I liked seeing? Vegetables, that's a great. I'm gonna go back to the belt. So that's like the first thing he did.
Now you'll see our muffin monster at work.
Oh yeah, that was like rocks or something. You just get undressed at night and put your clothes in there instead of washing them. We all need one of these, right? You know the guys who work at the sewer treatment plant are just constantly goofing off with the It's like the best thing in the whole place. All right. Well, thanks again, Yi. Let's close this. Let's see who's next. All right, Pufang, you're up. Here, you can put this on your lapel so it hear you.
Hello everyone, today I will do a presentation about the mixing and the flocculations in chapter 5. So what is the mixing in wastewater treatment? It is a very important unit in operations in many steps of wastewater treatment. So it includes mixing of one substance completely with others, blending of miscible liquids, flocculation of wastewater particles, and continuous mixing of liquid suspensions and heat transfer. So usually most mixing operation can be classified as rapid mix or continuous mix. The difference is if the detention time is less than 30 seconds, it will be the rapid mix. But if the detention time is longer than 30 seconds, it should be the continuous mix. So the rapid mix in wastewater treatment is useful for blending of chemicals with wastewater, blending of miscible liquids, and the dance of chemical to sludge and biosolids to improve their dewatering characteristics. And the continuous mixing in wastewater treatment is always used where the contents of a reactor or holding tank or bins must be kept in suspension. So the flocculation in wastewater treatment, the purpose is to form adrites or flocks from finely divided particles and from chemically distinguished particles. And it always be considered for increased removal of suspended solids and BOD in primary sampling facilities. And conditional wastewater containing center industrial wastes and improve forms of secondary sampling tanks following the activities sludge process and as a pretreatment step for the filtration of secondary effluent. And when I looking for a book, there are two steps of flocculations, micro flocculation and macro flocculation. But the pronunciation is hard for me. And 3 is the energy dispensed in mixing and flocculation. There are two tables of the energy dispensation. The first one is always used for the macro flocculations because the mm, the materials we can statistics can be statistics, but the table 2 where some like some quantum in the water, it will be the members will be huge. So if we use the like a G to figure out it will be hard. So the type 2 is for the micro flocculation. Like some results, maybe some 0.0000, many 0 be XB work for the type 2. And the types of mixer used for the rapid mixing in wastewater treatment. There are 5 mixer, and the static inline mixer, inline mixer, and the high-speed induction mixer, the pressurized water jets, and the tubing and propeller mixer. And the last one, tubing and the propeller mixer, is also a mixer used for the maintaining solid in the suspensions in wastewater treatment or some chemical mixing. And there are some pictures about its mixers. And 5 is types of mixer used for flocculations in wastewater treatment. They are buffaloed static mixers, and pedal mixers, and tubing, propeller, and hyperpolate mixer. And also there are some pictures searching on the internet about its mixer. 6 is types for the mixer used for the continuous mixing in wastewater treatment. They are pneumatic mixing. This is a process of mixing, and the mechanical alters, and the hyperbolic mixer. The hyperbolic mixer is also another types of mixer used for the maintaining solid in suspense in wastewater treatment or chemical mixing. And this is a picture of its mixer. And 7 is the new developed in mixing technology, like the first one, CFD, to model the fluid flow partners in mixing devices, and DPIV to understand the fluid movement in mixing devices, LDA to start turbulence and to obtain data on the main velocity. And the last one, LIF, measure the degree of mixing of solutions. Thank you.
Okay, so I'm going to talk about gravity separation, which is basically settling, and it's extremely simple as a general overview. You can get very specific. It can get actually kind of ridiculous, some of the things at first glance until you really study it and pay attention to it. But basically, it's just settling solids out. That's the whole point. But just to break it down just real quickly, gravity, basically, everyone knows what that is, I would hope. It's just, force pulls everything to the Earth's surface. For you metric people, it's 9.81 meters per second squared. I use the left the squared off there, but 32.2 feet per second squared. And I brought up the graphic from the movie Gravity, which is ironic because there's none in that movie. And then there's separation, the second part of it. It's just separating people or things. In this case, hopefully things. If you're separating people, wastewater treatment has gone really downhill. So basically you're just putting those two words together. You're using gravity to separate things. And in most cases, or in just about all cases, it's to separate water from the solids or whatever might be in it. There's a bunch of different types of separation. You have discrete particle settling, flocculant settling, ballasted flocculant settling, hindered settling, compression settling, accelerated gravity settling, flotation, and I throw no doubt settling in there just because the rest were kind of boring, so I thought that'd be a little bit more entertaining. But again, basically all of these are just different types of settling that uses the gravity to layer things. Basically you're pulling gravel, grit, whatever you may have out of the water and getting it to separate because the heaviest thing is going to sink. And for the most part, it'll get the bulk of things out of there. It won't necessarily get all the, anything that's suspended. It takes too long. So that's when you have to go down to the flocculant settling. Now what flocculation does is you're putting something in there, some type of additive to the water. It makes all of the particles cling together before they drop out. So you're basically taking the smaller particles that don't want to settle quick enough and you're making them one big particle, and then that way they're heavy enough they'll drop out. In the typical wastewater treatment process, this can vary vastly. This was just kind of a basic one that I pulled together. In pre-treatment, you have the screening that Wade spoke about earlier. Then you have the gravity separation, and in some, the activated sludge is not so much secondary as it is kind of a separate process. It drops out. The gravity separation occurs in the primary treatment, and it'll drop the sludge out, and then the activated sludge, or how you can go into activated sludge, or you can not have that step. You can actually just take the sludge out and treat the sludge separately. And then there's so many ways. It's really difficult. It's too much to cover in 10 minutes. Luckily, I'm just talking about gravity separation. But you can see it's usually your primary treatment. It's usually the main one that you're going to go with. And again, it's after screening gets the larger items out, this gets the stuff that makes it through screening. As a general rule, the reason it's important is when you get to the disinfection or the activated sludge steps and the steps beyond the gravity separation, the dirt can actually mask biological agents. So if you have, your biological, your diseases, your whatever microorganisms in your wastewater, if the dirt's in there, whatever you put in to disinfect it, whether it be UV or chlorine, just whatever you need to use to disinfect it, the dirt and stuff that's floating, say you have clay that is really difficult to settle out, it can actually mask that, and your tertiary treatment or your disinfection will not be nearly as effective. So you'll lose a lot of your effectiveness on down the line, which, for those of you not that familiar with wastewater treatment, that's the main reason you go through all these steps, is because the screening helps the gravity separation. Then the gravity separation helps the activated sludge. Then the activated sludge gets more out, it helps the disinfection. It's just taking it basically step by step. And right there, I just thought that was a nice looking primary clarifier. That's really just a settling tank. You can see it's got the arm going around. That's aerating the water, because mixing the air helps the gravity pull some of the particles out for a lot of different reasons. But this was just a nice large. That's actually, from what I read about it, I think it was a 500,000 gallon tank. And that was, if you go back, that's actually that same plant. They built a pilot clarifier way off to the right. This was kind of, I guess, just a pilot experiment. I don't really know. Didn't read that much about it. Again, I was just studying gravity separation, and that's what came up. So going back to, this is your typical shape. You have the point down here at the bottom. The solids will settle out, and they'll kind of go through a funnel almost. And that's how it drops out, and that'll go over into your sludge. But you can see you have the different layers here. The water on top is going to be your clear water, and that's because as it comes out the other side of the tank, I guess I should back up just a little bit. Basically, for most of this, water's just going into a big tank. and it's flowing across this tank, and it's slowing the flow down so much that things are allowed to settle out. Well, this kind of shows a breakdown line by line, but it's more of like an angular thing. Let's say it's flowing in over here and flowing out over here. You'd have dirty water here, and you'd have clear water up here. But then from there down to about there, you would have your discrete particles. That would be the smaller things, and then you have your flocculants kind of coming down, and the hindered. And these are actually the velocity. It doesn't layer quite like this, but it's a good representation of what is happening. And then down in the bottom, that's going to be really compressed. That's going to be the heaviest things have settled down to the bottom. They'll settle quickly, some of them. In West Virginia, a pretty standard DEP requirement are these tanks have 24 hours of holding time. That's kind of a minimum. If you want to use less than that, or you want to go way over that, you have to provide documentation as to why you're doing that. And the rest of the system has to kind of pick up the slack if it's less time, or sometimes you can get by with a little bit less secondary treatment if you have a longer time. But that comes down to money. How big of a tank can you afford? Obviously, it'd be perfect to have a tank like this. You know, clay is not going to settle out in 12 hours. However, if you could afford it, you could build in Charleston, a 50 million gallon tank, and by the time it gets across there, that's going to take, a few weeks. All of your clay would pretty much be settled out. So that's where you get into kind of a cost-benefit analysis. That's just a pile of stuff. That's your sediment right there. It's dried, I'm assuming. I don't think it actually comes out like that. It's a really good treatment system if it does. But in there, you're just going to have grit, your sand, your gravel, your smaller particles that weren't picked up in screening. Your TSS might be settled out in there for the most part. It'll get a percentage of that at least, if not all of it. And then any flocculants that you got to come out, whether it's biological or chemical, that's going to be mixed into that just pile of mess there. You can see some of it's shiny. It's a lot of, I would say the bulk of it is grit and sand and little small pieces of glass. Kind of, again, it's finer than the stuff you had than the screening. It would kind of be what would come out of like the macerator. It's not ground up, but it was just already the smaller particles. I didn't really want to go into the equations because this is more of an overview. In 10 minutes, it's a little tough to go into details. But you have your equation for it's the law of sedimentation. It's formed by Newton and Stokes' law. That's the background. So you have your gravitational force is what's going to be pulling it down. Then you'll have your density of your particles, your density of your water, acceleration due to gravity. I put it in metric for you there. And then the volume. It's a pretty basic equation. Again, when you're doing the design aspect of this, gravitational separation is really basic. It's an easy part of the design. It's more of a factor of how much are they willing to pay for, and if they're going to go cheap and do a smaller amount, then how are you going to pick up the slack later in the treatment process? And then I said that he's probably watching the clip of like the maciator. There you go. He's watching the monster, whatever it was, separate things. Anybody have any questions? I'm a little early here, but
That's fine.
Yeah.
Appreciate it, Lee. Very good. All right, Zach, you're up next.
One second, I noticed I left one button out there. All right, everybody, my name is Zachary Michael, and my presentation today is going to be on grit removal. Basically, grit removal is the process that comes right after screening, which Wade just went over previously, and the process before gravity sedimentation from the presentation we just heard. So basically, what is grit? Grit consists of all sorts of things. Basically, anything that gets past the screening device. Basically, the way it was put to me in my undergraduate wastewater class, screens are meant to keep out cars, people, anything real large. With the grit removal, we're more worried about the sands, the gravels, cigarette butts, eggshells, anything that just slips down into the sewer. Grit removal is necessary to reduce the formation of heavy deposits in aeration tanks, aerobic digesters, pipelines, and channels. It helps reduce the frequency of cleaning the digester, and also helps protect mechanical equipment from abrasion. Overall objective of grit removal is to remove all depositable grit during normal and peak wet weather flow, and to protect an endpoint suitable for landfill disposal. As you can see here, we have a little diagram of what goes on. The first part of grit removal is grit separation, then we go to grit washing, and then we got grit dewatering. And we'll go into these three a little bit later on in the presentation. So how is grit removed from wastewater? Basically, it goes through a grit chamber, which there are multiple types of grit chambers. The first and most common one in the past was a horizontal flow grit chamber. And along with that, you got rectangular and square horizontal flow grit chambers. The next and probably the more popular style nowadays is the aerated grit chamber. And a newer type of technology being utilized more and more and more is the vortex type grit chamber. Under that, they have the mechanically induced vortex, hydraulically induced vortex, and multi-tray vortex grit separator. So now we're going to go into a little bit more detail about horizontal flow grit chambers. And I do apologize, I cannot find a picture of a good representative horizontal flow grit chamber to show you all. But basically, the horizontal flow grit chamber is the oldest of the three technologies I'm going to show you for this process. They're kind of being limited now in newer treatment plants because of the use of the aerated and vortex style grit chambers. They're typically designed to remove all the grit particles retained on the number 70 sieve, from those of you who are familiar with your soil mechanics and being in the laboratory. However, many of them are designed now to remove grit particles retained on the number 100 sieve. Some of the benefits of the horizontal flow grit chamber is it exhibits flexibility and very easily constructed, and also with effective flow control, the chamber may be removed. However, there are some disadvantages. Velocity over a wide range of flows is difficult to maintain, and head loss generated is very large. With the aerated grit chamber, airflow is generated by a blower, which is then entered from the bottom of the chamber, causing a circular motion in the water and in the wastewater. The flow pattern causes grit to settle to the bottom of the chamber while keeping lighter organic material in suspension to go on to the primary sedimentation basin, where they'll handle that. Once the grit has settled, either a recessed impeller grit pump or an air lift pump is used to remove grit slurry and send it on down the line for the dewatering process. Some of the benefits of aerated grit chamber is the maintenance cost is significantly reduced compared to the other two types of grit chambers, and you get a consistent grit removal over a wide range of flows. One of the disadvantages, however, is potentially harmful volatile organics and odors may be released from aerated grit chambers. And as you can see up on your screen, we have two pictures. On the right, we have a little schematic showing the circular flow that from the air being sent up from the bottom, causing a circular flow. And this is a picture I found from one of our manufacturer websites. This is actually from a company called Westtech. I'm not sure if any of you are familiar with it, but they are a very large leader in producing grit chambers. So next, let's talk about vortex type grit chambers. Basically, screened influent enters tangentially and flows around the upper chamber, and adjustable rotating paddles augment the spiraling flow to create a mechanically induced vortex which settles the grit. Benefits of this is it reduces civil work expenses, low energy consumption, and efficient grit removal over variable flow rates. Some of the disadvantages, though, is it does require, some installations do require deep excavation, and the modifications are difficult to perform on this. We do have three pictures here. Here is actually on the right side of your screen. You can see one in action. It has getting the circular motion to it. I kind of just like this picture on the left. It kind of shows what's going on a lot better. You can see your water entering here. Around the top part of the chamber is being induced into the vortex. Your grit's going to settle out, and your effluent's going to go this way.
Some of the manufacturers that I found that produce grit chambers, West Tech, as I mentioned, is one of the biggest ones that I've noticed. Others, as you see, is Hover Technologies, Cortex, Toro, Wastewater Equipment Industries, and I'm not really sure how to say this one. I would call it Ecoton Industrial Group. So as mentioned previously, the grit removal is a process. The next part of the process is the grit washing. After we separate, we're going to send it off to washing. And it's basically to help get the volatile solid separations. Grit is separated from the main wastewater flow and is transported in a slurry to the washing process to remove some more organic material. Objective in grit washing process is to achieve a clean grit with a low volatile solids content. Generally less than 20% is what most treatment plants are aiming for. There are two types of grit washers. One relies on an inclined submerged rake that provides the necessary irrigation for separation of the grit from the grit, put that in there twice, the organic material, and raises the wash grit to a point of discharge above the water level. The second type just uses an inclined screw and moves the grit up the ramp, and then it will go to the drying / dewatering phase. Dewatering is important due to a lot of the environmental regulations being placed, especially at our sanitary landfills. Once the grit is dewatered from all free water around the particles, it must be able to pass a paint filter liquid test. Did a little bit of reading about this. Basically how this test works is you just grab a paint filter, take a random representative sample of your grit, place it on top of the paint filter, wait 5 minutes. If any liquid is to come out of the bottom of the filter, then your test fails. If nothing comes out, then you pass. A very simple test, doesn't require any fancy technologies. This is just to make sure that no liquids are getting out into our landfills. Again, the objective is to produce a clean, dry grit, total solids concentration greater than 60%, while retaining at least 95% of the depositable grit. A few design considerations. Design of grit chambers are based off the peak flow rate that will enter the grit chamber. We can't design off the normal day-to-day flow rate that we see. We want to design for the worst case scenario for the whole treatment plant. The forward and horizontal velocities must be sufficient to maintain organic solids in suspension, but low enough to permit settling of the grit particles. Average design velocity is 1 foot per second from what I've found. Grit chambers should be designed to provide 1 to 5 days of grit storage. As mentioned previously, if money wasn't an object, we could design to store for 25 days, I'm sure, but this is just to be the most cost effective. Depth to width ratio should be between the 1-to-1 range and the 1.5 to 1 range. Area grit chambers generally are designed for the detention time of 2 to 5 minutes, and cross-sectional area, length, width, depth are all designed based upon the peak flow rate conditions. And that is all. Thank you all.
Hello everyone, my topic is primary sedimentation. And the primary sedimentation is the first step in the photo processing after the pre-treatment stage. So the pre-treatment stage will be the coarse grain to pine to fine grain to grit tank. And after that, the wastewater will go to the first treatment stage, that is primary sedimentation tank. The objective of the primary sedimentation tank will be remove the readily settleable soil and the floating material found in the wastewater, and they reduce the suspended soil and in the contact. So the efficiently designed the sedimentation tank can be removed the 50% to 70% of suspended salt and 25% to 40% of BOD. So I'm going to talk about the two types of the sedimentation tanks. The first one is rectangle tanks, and the second one is circular tanks. How to select the type of sedimentation? It depends on the site of installation and the rules and regulation of the local control authority and local site of condition and the experience and judgment of the engineer. So you can see the two tanks in the picture. And from the picture, you can see the primary settling basin. It has 4 parts, and the here is the inlet part, and this is outlet part, and this is the settling part, and you can see the sludge storage part here. And there was two kind of the collector using the rectangle tanks, and that is chain and the flight salt, and the other one is traveling bridge type of collector. I just can't find a picture of the chain and the flight salt, so it's this one. You can see the endless conveyor chain. This one, it will go to the surface of the wastewater and goes and collects the salt, suspended salt, and goes to down and collect the sludge and sludge to the hopper. And there is some important issue with the rectangle tanks, and the first one is sludge removal. We commonly use the mechanical sludge removal, and it will scrap the sludge from the collectors, which is Buffalo and others. And another one is a flow distribution. Flow distribution is the critical part in the rectangle tanks, and and there is some important parts of the flow distribution. That is, you must careful about the vertical velocity, or if you didn't pay attention to that one, it will be resuspended the salt in the bottom. And another is handless and the hydraulical profile. And the last one is scum removal. Scum can be removed removed hydraulically or mechanically, which is scrapped from the collector or water supply. Now I'm talking about the circular tanks. Circular tanks pretty much like rectangle tanks, and it also have 4 parts: the inlet part, in outlet. Oh, it's not outlet part, and this is settling part, and this is a sludge stored part. And it also have 3 important consideration. And the first one is the flow pattern. Circular tanks is a radial flow pattern, and it commonly type is a center feed type of the circular tanks. And another is energy dissipation, and the last one is sludge removal. In the circular tanks, we also can use the airlift pump to remove the sludge. And beside the rectangle and the circular tanks, we also tanks of the sedimentation, and we also have the combination flocculator caliper, and this one is used for enhanced settling, especially in the industrial water. It needs industrial wastewater. It needs more times to settling the suspended salt and others. And also, if you add the inorganic chemical or ployer, it can be improve the flocculation, which can enhance the settling. And another one is jagged caliper. This one is originated from the Japan, called the limited area, but it also used in the United States, which is a Deer Island wastewater treatment plant in the Boston Harbor. There is some element which is affect the performance of the sedimentation tank, and the first one is the eddy current formed by the inertia of the incoming fluid, and the second one is the wind-induced circulation cells formed in the uncovered tank. The third one is thermal current. The fourth one is cold and warm water causing of the formation of the dusting current that move along the bottom of the basin, and the warm water rising and flowing across the top of the tank, which is mean temperature. And the last one is the thermal stratification in the hot and arid climate. Those all will reduce the removal of the BOD and the TSS. That's all I'm talking about the sedimentation part. Thanks for listening. Thank you.
All right. Jen?
High-rate clarification employs physical and chemical treatment and utilize special flocculation and sedimentation system to achieve the rapid settling. This is a picture I found in Google. I think it's from a company called Active Floor, and it is set up in 2008. In the textbook, it said this type of high-rate clarification is always used in Europe country for almost 15 years, but it has just recently introduced into America. Since this company is set up in 2008, I think maybe something wrong with the textbook. This? And the essential elements for the high rate clarification is first is enhanced particle settling, like this. Yes. And then the enhanced use of the inclined plate and tube settler. It's all combined in the three type of basic clarification. And the advantage of the high rate clarification is that the first one is the units are compact and thus reduce the space requirement, since now big cities are always lack of the space, and the smaller the facility, the better the usage. And the second one is the setup times are rapid to achieve the peak efficiency. The third one is it will get a highly clarified effluent in product. And this is enhanced particle flocculation. Involves the addition of an inert ballasting agent and polymer to coagulate and partly flocculated suspension. And you can see from this picture, this is how the plurality layer worked. It combines together to gather the sand grains. The polymer layer is worked like a glue to combine these micro sand into flock particles. But in the third type of the flocculation, there are three basic types. In the third type, it working another way. I will talk later. And the analysis of the plastic particle flocculation and the settling velocities of the particle is increased when compared to an unblasted flock particle. Several ways. The first way is to increase the density of the micro sand, and the second way is to increase the Reynolds numbers, and the third way is to decreasing the shape factor through the formation of more dense spherical shaped particles. And the blast flock particle appears to be more spherical than the flock particle long. This is, like I mentioned, the three basic types of process used for high rate clarification. And as I get from the network, the first one and the second one are used mostly, and the third one, I didn't get too much information for the third one. Let's jump to the to the first one. It's better. Like you can see, the first one is called the blasted flocculation with limbed lamellar plate clarification. This one employs a proprietary process, which flocculation aid and blasting agent are used to form density microflow particles. In the first type and the second type, those blasting agents are always used to form the dense microflow particles. and thus make the particles to settle rapidly. This treatment consists of three components. You can see from like the three zones. The first one, but it's not always the three zones. It depends on the manufacturer, or there are some or other needs. It's sometimes like two zones. Sometimes they can just put all three zones together to force just one zones. And the second one is a three-stage flocculation with lamellar plant clarification. Like the structure is somehow like the first one, and also the three-stage. It depends on the manufacturer, and as I found from that company I mentioned, the RT-Flow, they use a two-stage. Maybe its efficiency, and you can see there is a clarifier underflow. The flow enters in this content in this zone, and after this part, it recycled to the zone again to enhance the speed of the thickener. And when talk about the third one, it's called the dense slug. The process this is a process property and differed from the first one and the second one. The chemical conditional solid are used to form microfloc particles with incoming wastewater instead of microsand. The first one and the second one use those agents to form the microsand, but this one is use them to make the microfloc. The influent wastewater entered air mixer zone where great separation occur and the coagulant is injected. After mixing, the wastewater flows into the first stage of a two-stage flocculation tank, where polymer is ended together with a chemical condition recycled solid. I think. And there is a summary of the feature of the high-rate clarification process. There are three types, and each one has like the first one, it's microsand provides a new seal for the flow formation. The flow is dense and settles rapidly. Lamellar clarification, when used, provides high rate settling in a small tank volume. And the second one, the three-stage flocculation enhances the floc formation, and the lamellar clarification provides high rate settling in a small tank volume. Somehow the first one and the second one is somehow the same, and the third one is different from those two. Settled stock solid are recycled to accelerate floc formation, and the dense floc is formed that settled rapidly. Thank you. That's all.
Hi, I'm Matt Tanner. I am going to be talking about flotation. Now, what is flotation? Flotation is a treatment process that's used to remove solid or liquid particles from a wastewater using the introduction of tiny gas bubbles into the wastewater. As the gas bubbles rise to the surface, they attach to the particles and carry them with them, or they increase the buoyancy of the particles and carry them to the surface. Once they reach the surface, a skimmer system is used to collect the material for processing or disposal later on. In this picture right here, you can actually see this is the skimmer system, and this yellowish material back here is the particles that have been brought to the surface. Flotation is typically used in applications where you need to remove total suspended solids, oils and greases, such as industries where you may have food and beverage manufacturers or oil and gas operations. It's also used in municipal operations to thicken the sludge. In some cases, flotation may provide better removal of particles than sedimentation, depending on the constituents in the wastewater. If you have very tiny particles that may settle slowly, the flotation process could be used to bring those to the surface where they could be skimmed off more quickly than they would otherwise. If you have particles that are actually less dense than water, such as oil, those will over time come to the surface, but the flotation process can be used to enhance that and reduce the retention time that's required. Now, if you have a wastewater that has both types of particles, you will have particles trying to move in opposite directions, which will not work very well at all. By using flotation, you can get everything moving in one direction, bring it to the surface, and get it skimmed off. Now, to aid the flotation process, chemical coagulants or flocculants may be needed. Inorganic chemicals like ferric or aluminum salts may be used. In those cases, they actually create a structure around the particles that can entrap the air bubbles. You may also use organic polymers, which actually change the interface between the liquid in the wastewater and either the particle or the bubble, or in some cases both, and increase the attraction between them. Now, there are multiple types of flotation processes. The three main types discussed in the book are the dissolved air flotation, dispersed air flotation, and the charged bubble flotation. They're all very similar in how they work. The main difference is how those bubbles are formed. In general, from what I've been able to read, it appears that the smaller the bubble, the higher the efficiency you're able to achieve in removal. And here you can see that the dispersed air flotation of the three has the larger bubbles, whereas the charged bubble flotation actually has the smallest bubbles. And this picture over here is actually a dissolved air flotation unit under construction. So first we'll talk about dissolved air flotation. This is probably the most common flotation process used. In this process, air is dissolved into the wastewater through pressurization. Then as the pressurized water is discharged into the flotation tank, the pressure drops, and the air that has been absorbed into or dissolved into the water comes out of solution and rises to the surface. And you can actually see a similar reaction occur sometimes if you've poured or got water out of a tap, especially hot water. If at first you'll put the water in the container and it may appear cloudy, but over time you'll see it slowly clarify from the bottom up to the surface, and that's bubbles coming out of solution and going to atmosphere. Now, for the dissolved air flotation process, there are two setups. For smaller flows, the entire flow may be pressurized and held in a tank for a few minutes while the air is dissolved into the solution prior to discharge to the flotation tank. In larger flows, only a portion of the treatment unit effluent is recycled back through a pressurization tank where the air is dissolved, and that is then injected back into the influent flow prior to entering the flotation tank. So here we've got a couple of flow diagrams from the textbook. Here you can see addition of coagulant goes through a mixing process. This is actually the direct pressurization setup. The entire flow goes through the pressurizing pump and into the tank. It then goes through a valve into the flotation tank. The bubbles rise to the surface, and here you can see a skimmer at the top which just rotates, and the paddles carry it to this overflow. There's also a baffle in the tank where the water flows underneath to prevent or help minimize mixing of particles into the effluent. And here is a recycled pressurization system. Now you can see it's very similar. The main difference is that rather than going directly into the pressurization tank, it goes into the flotation tank. But here you see the recycle line, which again takes a portion of the effluent, brings it into the pressure tank where it absorbs air, and then discharges it into the influent line. The next type of flotation that the book discussed was dispersed air flotation. It's also known as induced air flotation. Now in this case, it's primarily used in industrial applications, but this setup here, there's an impeller which is used to pump the liquid, and when it pumps the liquid, it actually creates a vacuum up in the standpipe, which pulls in gas. That gas is mixed with the liquid, and as it passes through these dispersers, it forms fine bubbles which rise to the surface, and the foam or the material is collected by these skimmers for disposal. Also in this process, from what I understand, there are typically a series of cells that the wastewater will flow through of a similar process before leaving the treatment unit. Now here are a couple of examples that I was able to find from Siemens of dispersed air flotation tanks or dispersed air flotation units. Now this one up here, it appears as if, based on these hatches, that these are the different cells in the unit. Here's another example down here, and you can see a little cross section here in the corner, which looks it's very similar to the example in the text. Now the last type we'll talk about is charged bubble flotation. It's also been referred to as suspended air flotation. Now in this case, there's actually a separate bubble generator which creates a suspension of micron-sized bubbles which are coated in a thin film using a surfactant. These bubbles are then injected into the flow prior to reaching the flotation tank. Now this film may be adjusted based on whatever constituent you're trying to remove to either be anionic or cationic to fit the application. One advantage of this process is that because the bubbles are similarly charged, they're less likely to come together or coalesce. Yet at the same time, they attract the oppositely charged particles in the wastewater that you're trying to remove. And actually this right here is a picture I found of the bubble generator. And here's a flow diagram from the textbook. You can see a coagulation tank. From there, it's discharging to the flotation tank. However, in the middle, you have this bubble generator, which injects the suspension of film-coated bubbles. Again, similar to the dissolved air flotation, the bubbles rise to the surface and a scraper removes the material. So as engineers, what do we need to look at when designing a flotation process? In general, we need to look at the concentration of the particular particulate matter in the wastewater. We also need to get an understanding of how quickly the solids are loaded, are coming in, and the quantity of air used. We also need to get an understanding of how quickly the particles will rise to the surface when they are attached to the bubbles. Other factors that may come in or need to be taken into account are the flow rate coming in. You need to know how large of a tank you need. You need to understand the charge characteristics of the particulate matter. Are the bubbles going to attract what you're trying to remove? You need to understand the temperature of the flow. This can affect both the amount of air that could be dissolved into or gas that could be dissolved into the liquid. It can also affect if you say you are trying to remove an oil. Temperature can have an effect on whether that's becoming a solid or becomes, I guess, more of a liquid phase. We also need to understand what are our effluent parameters that we're trying to reach. If in an industrial application, you don't necessarily need to get it pristine, but you need to reach certain permit requirements. So depending on what those requirements are, you can size the treatment unit to achieve that. And then finally, what space do you have available? Those flotation tanks can come in various sizes and shapes. They could be circular, they could be rectangular. There are some dissolved air flotation tanks that have inclined plates inside of them and are really more vertical than they are horizontal. So what kind of footprint is available within the facility you're trying to place this? As far as dissolved air flotation systems, the performance really depends on the ratio of the volume of air that you use versus the mass of the particles. So that needs to be taken into account. But really, in all cases, every wastewater is different. With all of these variables, treatability and pilot testing needs to be done to reach an optimum performance and an optimum design. Here we have an example from a company called Heron Innovators, which actually produces that charged bubble flotation tank or system. This is a pilot treatment trailer that they have for designing these systems. Then here I just have a list of manufacturers. This is by no means comprehensive. If you search for dissolved air flotation systems, there are numerous companies that come up. These are just some of the companies that I used as references for information or of the pictures in the presentation. We also have a couple of companies which provide dispersed or induced air flotation systems. And I was actually only able to find one company that supplies the charged bubble or suspended air flotation systems. And I don't know if that's just because it's relatively new or it's just not widely used. And then just a list of references that were used. All right, thank you.
Last one.
My name is Selena, and today I'll be talking about aeration system. So what is aeration? Aeration is the process of bringing water and air into close contact in order to remove dissolved gases such as carbon dioxide and to oxidize dissolved metals such as iron and manganese. Looking at the picture, we can see aeration is after the primary clarifier. So it is a major unit process at the water treatment plant, and it is generally not needed for surface water supplies, but it's almost always required for groundwater sources. So moving on to the purposes of aeration, there are about few purposes of aeration. Some of them are to oxidize iron and manganese from divalent state to higher oxidation state, to remove undesirable gases from groundwater such as hydrogen sulfide, carbon dioxide, and methane, and also to remove volatile organic compounds because they cause taste and odor problems and they are carcinogenic, to add dissolved oxygen for taste purposes, and to add carbon dioxide because after lime soda is accomplished, pH of water is really high, which is greater than 10, so it needs to be lower, so that's why we add carbon dioxide. Moving on to the function and process of aeration. The function of aeration is to introduce air and water through the most effective and least costly methods that will increase oxygen transfer and in the wastewater. So the process of aeration is air pumped into the large aeration tank mixes the wastewater and sludge that stimulates the growth of oxygen using bacteria and other tiny organisms that are naturally present in the sewage. These beneficial microorganisms consume most of the remaining organic materials that are polluting the water, and this produces heavier particles that will settle later in the treatment process. Wastewater passes through these bubbling tanks in 3 to 6 hours. Here's a short video of how aeration looks like.
We've always got such jazzy music for wastewater treatment videos. It's classy. We're in the classy industry, right? Exciting, upbeat.
And it's also an ad for the ABS manufacturer. And there are two basic system of aerators used today. Those are waterfall aerators, which involve drops of water surrounded by air, and some of those, the types of waterfall aerators are spray, casket, and tray. And the injection aerators, which involve bubbles of air surrounded by water. These two are the types of aerators we study in this course. Diffuse air aeration and mechanical aeration. And here's a table from our book. Aerators are classified into different categories, and for example, diffuse air comes under submerged, and there are two types of diffuse air aerators, like fine bubble which is used for all types of activated sludge processes, and coarse bubble, which is used for activated sludge processes, channel and grit chamber aeration, and aerobic digestion. Diffuse air aeration. In diffuse air aeration, air and pure oxygen is introduced in the wastewater with the submerged diffusers or other aeration devices. Like said in the previous slide, there are two different types of diffuse aerators, fine bubble and coarse bubble. And the first picture is how the diffuse air aerators looks like, and the second one is how aeration looks like. And mechanical aeration. Mechanical aerators consist of mixtures of brush rotors that transfer oxygen into the wastewater by spraying the wastewater into the air. They use a mechanical agitator to force air into the water. The third picture is an example of mechanical aerators. Mechanical aerator can either be submerged or surface designed, depending on whether certain systems require pure oxygen to be introduced from aeration tank bottom. There are two different types of mechanical aerators. Vertical axis aerator, which induce updraft wastewater flow or reverse downdraft flow, and horizontal axis aerators, which spray water across wastewater surface to agitate water and entrain air into the water. The first two pictures are the mechanical aeration. Moving on to advantages and disadvantages of waterfall and injection aerators. Waterfall aerators have a large AV ratio, but the aeration time is very short and high head losses involved in its operation. Whereas injection aerators have the aeration time is long, but they have low AV ratio and high power consumption in its operation. Cost and design of the aeration. Aeration system, they consume approximately 50 to 65% of the net power demand for a typical activated sludge wastewater treatment. So the designer is responsible for selecting a system that is least costly. And comparative cost for different types of aeration system will be estimated once the requirement for the aeration are determined. Construction cost mainly consists of aeration basins, air piping and headers as appropriate, aeration devices and their supports, air cleaning equipment, blowers, and buildings to house these items. Operation and management. Operation and maintenance. Operation and maintenance costs are primarily for power, cleaning, and replacement. Operation cost is determined in part by the oxygen transfer efficiency of the fine bubble aeration system being used, as well as the characteristics of the influent wastewater. Aerator cleaning cost depends on the aerator type, how easily the aerator can be removed, cleaned, or replaced, and the plant's operation and maintenance procedure. And I conclude by saying that diffused air injection is the best for oxygen transfer, whereas coke as the injection aeration is the best for iron and manganese oxidation.
Thank you.
Mhm.
Okay. Well, very good. Thank you, everyone, for your presentations. How about this? Let's take a 5-minute break. Everyone can stretch their legs, get a drink, and that sort of thing, and then we'll get back together and take a look at an in-class exercise that I've prepared for tonight.